this idea that each region of the brain and each layer of a deep net is representing information in a completely different way, that just doesn't turn out to be true. There are a treasure trove of insights in neuroscience and cognitive science that can be assessed with a new lens by being a little bit creative on how you use deep nets.
This is Brain Inspired.
You ever notice how when you give directions, you don't ever use tiny landmarks? Like, follow that road for 40 miles and then take a right when you see the can of soup. Or how if I tell you the story about the time that I got attacked and mangled by an animal that may or may not have been a pet turtle, you picture some kind of creature like a turtle. Or how I'd never ask you to hang on to this mountain for just a second while I pick my teeth with a steak knife or something. Well, Talia Konkle thinks about these things, maybe not these exact things, and she thinks about brains. And it turns out that's a good combination of things to think about. In Talia's case, it means thinking about how our visual stream is organized in terms of what kinds of things are represented as one moves up the classic ventral visual stream hierarchy from low-level features like the edges and orientations of Hubel and Wiesel up to the higher-level full-on objects. She calls it a tripartite organization because she has found that our brains make distinctions between big inanimate things, small inanimate things, and animate things, like animals, basically. And she even invented a tool and a word to name that tool to study these things. So we talk about all that. By the way, I am Paul Middlebrooks, and welcome everyone to the show. We also talk about how she's used deep learning networks to study this tripartite organization as well, based off of some of the work of my previous guests like Marcel van Gerven and Dan Yeamans. We talk about how deep learning has actually changed the way that at least some people even teach visual neuroscience, which is an interesting thing I hadn't thought about. Talia will be giving a talk at the upcoming Cognitive Computational Neuroscience Conference in September. So we talk a little bit about the conference. And to remind you, you should check that out at ccneuro.org, where you'll find videos of the talks given during all the previous years of the CCN conference. And soon you'll find a video of her. I will link to the conference and all that we talk about in the show notes at braininspired.co/podcast/44. Stay well, dear listeners. I have appreciated all of the support and the emails I've been getting with questions and suggestions for the show. I make this thing for you and for me. Obviously, it's not for a general audience, but a curious and already rather knowledgeable audience, that is you. So I hope it hits you in just the right spot. Okay, here's my enjoyable conversation with Talia Konkle, whom you can also find on Twitter at Talia_Konkle. Talia, thank you for being on the show and welcome.
Thanks for having me.
I can tell in my visual stream you're an animal. So just a little foreshadowing there. I couldn't resist.
It's true. Critical division. Success. Consider your visual system working pretty well.
Yes. You are an animal who is also a principal investigator. You run your lab. You run your cognitive and neural organization lab at Harvard, where you use behavioral experiments and fMRI imaging and modeling to understand how the things that we represent in our minds physically are mapped in our brains, essentially.
Yeah.
To ask those questions, you use visual processing, in particular, how we represent objects within the ventral visual processing stream. And maybe another way to say what you do is that you're discovering how our story about the ventral visual stream is wrong. Would that be accurate?
Well, we'll just add an updated layer. I think that there's something to the hierarchy, the visual hierarchy. That's sort of the classic story of how information gets routed from our eyes up, through the ventral stream into higher level representations that help us recognize the world. Mm-hmm. And I think that's gotten us a really long way. And I think that there's real truth to it, as evidenced by all the successes in deep learning that are taking advantage of that kind of architecture. But I think it's just only half the story. And so I think I try and think about what we can learn from the other half, because the cortex is two-dimensional and the hierarchy is only one axis. So I think about how things are mapping along the other axis and what kind of insights we can get from that.
Yeah, and one way to say that, and we'll dive more into this later, I suppose, is that the visual stream research has focused on, let's see, I guess that would be latitude, and haven't looked at the longitude, for instance, or vice versa. So that's an interesting, I wouldn't say short-sightedness, but it's an interesting development. So you mentioned deep learning, and this is a show about sort of the intersection of artificial intelligence and neuroscience. And I have heard you say for a long time there was like a certain way to teach the introduction to visual neuroscience. And now that deep learning has come into our world, that way to teach it has been altered. Could you elaborate on that? How has it been altered?
Yeah, sure. I mean, one of the things that you have to do when you teach a class in cognitive science or cognitive psychology or vision is you have to introduce the problem of vision to people who've maybe never thought about it. And the problem of vision is, that you think you just see the world directly. Like, of course, those are objects and scenes and people in it, but that's just the mental model and a construct in your head. You don't actually look out at the world. Light comes in to the system and it's constructed to form this rich model that helps us actually act in the world. We don't directly see the world itself. And so that's the problem of vision. And it's hard. It's so easy and effortless, but we can't even make machines do it. So that was like the standard story of convincing people, young minds coming in to learn about cognitive science. Like, the vision is a really interesting problem. It's so hard. We can't even make machines recognize objects.
Right.
That whole motivation for why it's fun to study vision is completely out the window now. But we have a similar motivation, which is like, the problem is so hard that we couldn't make machines do it until 5 years ago. And now there's a huge, confluence and, all kinds of cross-disciplinary insights going back and forth between machine vision and human vision and biological vision to try and understand what's going on. So it's still a very exciting time to be studying vision, just for different reasons than maybe a few years ago.
Well, and you can say, and damn it, it is still hard.
And it's still hard.
That
it's easier than it was before, or at least there's new ways of approaching it.
Nice. Yeah, I mean, I had not thought of that, and I heard you mention that. I think you're in a discussion panel or something, and I thought, wow, that's a real big deal to change sort of the paradigm. Yeah. So yay, deep learning.
Every intro lecture. I know, it's exciting.
Yeah. So hey, you're going to be giving a keynote address here in a month and a half or so in Berlin at the Cognitive Computational Neuroscience conference. And that conference is about bringing together people from the brain sciences and from the AI sciences, essentially. I mean, so you've been in panel discussions about these things, and you've had a bunch of abstracts. Actually, you presented a bunch of abstracts last year at CCN. What is your take on how cognitive science and computational neuroscience and AI can best work together?
Ooh, that's a really good one. I mean, one of the interesting things is that we're still figuring out how, and the number of ways and that they can inform each other is still sort of unfolding. I think if I had to put one principle out there for people interested in this interdisciplinary intersection, it would be to sort of treat all the fields as equal partners in the quest for insight, because it's easy to think of the advances in the other field purely as tools. So I care about the brain, and I'm going to use machine learning insights to care about the brain. And so I need someone to help me to just do my models. And that's sort of like a it's not sort of respecting the insight and innovation on the machine learning side. And then it goes the other way too. Like, I want to make a model perform better. I want some insights from brain science, but I don't actually want to I just see if you can tell me how to understand my model, but I'm going to build it this way or something like that. So there's like room. And honestly, I think if anything, it's more this is my view, but the neuroscientists may be wanting the machine learning tools and need to get those skills. And I think the most important thing is to actually respect the innovations and insights on both sides and sort of find our way together. So it's a real convergence rather than a sort of usurping or sort of a tool use without really sort of benefiting from both sides. So that's very general advice, but
it's an interesting question whether that approach will effectively speed up, will herald a more effective research approach, right? So it's either borrowing the tools or diving in and a full-fledged respect, for both sides. So
exactly. And maybe in truth, as it often is in science, like you need all the ways. You need the people who use it as tools, and you need so that's a less interesting answer. But usually it's true. Like, thank goodness we have people who want to use it as tools and people who want to dive across, and that like actually it's the set of all of these approaches together that are important. So it's not a great answer, but where I land is to try and really deeply engage in the other side and try and pull as many cross-disciplinary insights as is possible.
A respectful animal you are, it seems.
Yeah, I try.
What are you going to be talking about? Do you know? I mean, I know it's still, there's plenty of time.
We have weeks left to sort that out.
I know.
I know the pace of projects is interesting. I never actually quite know what I'm going to talk about till a couple of weeks before. Yeah. And so I think I have at least 2 weeks still to hit mission critical. Yeah. But yeah, I think there's sort of maybe 2 broad areas that I'm excited about in terms of directions my research is going and projects to that end that will make it in, or somehow make it into the talk, or maybe one of them will.
Is one of those the visual stream, the ventral visual stream story that we might talk about today? A little bit? Yeah,
that's right. So one is about like the importance of topography in brain organization and what insights we might get into understanding brains by thinking about topography, and sort of thinking about how we might add those to Deepnets, which don't have a lot of topographic constraints.
Right. Okay.
And then the other is about what's the goal of the ventral visual stream in the first place. I mean, there's been a lot of focus on object recognition, and it's got us pretty far, but I think we're starting to move past that and think about what other goals might give useful feature representations. And so we've got some work on that end as well. So it's to choose your own adventure. Which would you prefer?
Yeah. Oh, is that how you're going to present it at the keynote?
Well, no, I don't know yet. I have 2 weeks to figure it out.
That would certainly be memorable. What would you guys like me to speak about?
Just prepare one talk or the other. Yeah. Risky. I don't think I can pull that off yet.
What is the most critical open question that's driving you these days in your research?
Yeah, those two.
Yeah. Well, that's. Yeah. I mean, obviously, right? I mean,
that's where we're going after. Like, what's the real goal of vision, and how should we think about moving that forward now? And then. For me, I've always loved topography and why things are where they are. Is that happenstance? Is that arbitrary? Is it informative to the function or the nature of computation? And I think that those are really deep and hard questions, and to answer them requires, development and thinking about evolution and, computational models of features. And it's just a really rich question to try and get sort of normative style ideas about why the visual system takes the form that it takes. So that's what I think is the critical open question that I'm interested in.
The evolution route is always fun because there are just so many just so stories that you could tell yourself. And so you have to be really careful. But you can make a good story, for sure.
That's true. I know. I actually think that Deepnets are kind of an interesting opportunity to start to provide different ways of thinking about how things are the way they are. So there's generally the empiricists who think much of the structure is learned, on top of a very general purpose architecture, and the nativists who think, well, the architecture is very specialized to what we do, and experience comes in and just sort of fine tunes it, but it's already in there. And there's many just so stories and models to either end, but I feel like Deepnets have really are sort of like an empiricist, new tool to really go, well, what is learnable from what kinds of input and how sparse a feedback signal? And so I think that there's room for sort of modeling developments that start to operationalize some of those just so stories to go, well, what if the signal that helps train the network is, something like animate, inanimate, rather than 1,000-way object categorization, or, these kinds of things become operationalizable in a new way, or what if the network only saw this much, what could it learn, with this kind of architecture? So I think those are like new, or at least new for neuroscientists coming in these tools and sort of thinking about how we can operationalize some of those stories.
So that leads to my next question, actually. I mean, it sounds like, so we have these deep nets, which is like a shiny new tool for neuroscientists, essentially.
Yeah.
So the next question is like,
respectfully.
Yes, of course.
Yes.
Of course. I don't know though. Well, I'll leave it for later.
Okay.
But my disrespectful. No, not disrespectful.
We'll get into that.
No, okay. I was thinking about how neuroscience progresses versus how AI progresses, and as a neuroscientist, I feel extremely jealous, essentially, of how AI progresses because
they're
fast. They're fast because they don't need to know how it works. Essentially. Anyway,
they're coming around to it. They're starting to know. They're starting to realize they need the tools of cognitive science. It's really exciting.
Well, that's true. But I maybe to clarify and this really is a tangent, so we won't go far. But so in neuroscience, progress means understanding like how it works, right? And in AI, understanding how it works is like nice.
Secondary.
It's secondary, but getting it to work, just solving the problem that you're trying to solve, that is the standard for progress. And in many cases, and I'm not denigrating, the difficulty of it at all, but that's just a much clearer answer.
Yeah, in that sense, it does. That's like, does it beat top performance? Is it state of the art? Check. Moving on. Next question.
Right.
I mean, I've also even seen on Twitter some people in that community expressing remorse over that being the standard and wishing it was a little bit more mechanistic. And I've heard that sentiment independently a few times. So who knows?
Yeah.
There's room for, maybe that could be something that we cognitive neuroscientists sort of help give back.
I hope so. Yeah. But so anyway, the question is, what do you think that we need more of to address what you're seeking to address, the questions that drive you? Do we need more data, better theories, better models, better experiments? I know we need all of it, but
yeah, we need all of it. But let's see. I think among the top sets, one, I think the idea of doing experiments on models, is something that's maybe not quite made, hit its heyday yet. We do experiments on people or in brains, and we get measurements, and then, but why not do the same thing with the model? So treat the model as a model system and give it different visual diets and see what kinds of representations it learns, or compare what's learned across different architectures. That's just studying the models in and of themselves. And that's like maybe a bit of a contrary thing for a cognitive neuroscientist to say. Like, that's interesting to me, though, independently of whether it matches human brains or matches human minds. Right. Just understanding how the models themselves are working and whether they're similar or different, and how, I think, is going to be really important in making the connections. And those are experiments that you can do, in a sort of less time and time limited way, because, you just run it on your GPU. You don't have to stick someone in the scanner to get those measurements. So I feel like there's more room to do experiments on models, just for the sake of understanding the models. That and massive human fMRI data sets. But I think those are underway. So
yeah, those are
people
underway.
are working on that. That's
right.
Yeah.
Kendrick Kay does that sort of stuff. I had him on the
That's
show.
right. I just saw him give a talk on it. Really,
is that right?
really cool stuff. Yeah, for
Cool.
sure. I'm glad they got him. I'm glad he's doing it because he's doing it well and right. And it's going to be high quality, high reliability data. So it's going to be really valuable to the community.
I mean, in some sense, the Deepnet approach to the doing experiments on the neural networks is sort of a neuroscientist's dream, at least from my perspective, because you attack, let's say you're, for me, recording in some area of the brain, but then you still don't know. The brain seems like such an unconstrained thing that we don't know about, whereas a neural net, you at least like have it constrained and like you kind of have the whole thing there. Yes, there's a lot to learn about it, but it's not a brain. Like you don't have to consider all the things that you really don't know about it. So
yes,
anyway,
that's right.
So
and exactly. And then I think that is the rub that I think is off-putting for some cognitive neuroscientists, which is it's not a brain. It doesn't have like a thalamus. It doesn't have laminar structure in the ground. I mean, there's like any number of architectural motifs that, may or may not be super critical for function. And so I think a lot of times the idea of like studying the network in and of itself can be sort of jarring because it clearly isn't like a brain. And so what's the point? But I actually think that reduced complexity is like critical. Yeah. And as long as you don't get confused, like what I'm studying is how the model does this. And that's interesting for other reasons than direct inference about brains. Then I think you're in the clear. And so exactly those ideas, like you can just understand, you can probe it to death and figure out, what's doing what and what are the information in the weights and how are those represented. And I think it's just, we haven't even begun to scratch the surface.
We're going to lose you to the AI side. I can tell.
Well, the sneaky thing is really, I still care about how minds and brains are, why they are the way they are. And the reason why I want to study machines is because I think they'll give us insights into the human mind and the brain. So I do think I keep my strongest foot planted here. I just think that there's quite a lot to learn from the other side.
Yeah. Well, that's why we're here today. So what's is there something that you want, that you're, looking to take home from a conference like CCN?
Yeah, I can think in the same theme because it's a new convergence. No one even knows how we should or ought combine these. Like in every week, there's a new paper where someone's done an interesting thing in a different way. And so, and it's impossible to keep up with them all. It's too fast. Yeah. And so I kind of use the conference as a curation for collecting insightful approaches for how I might try and compare across, minds, brains, and models. So it's sort of like a shortcut to the literature.
I think that's great. I mean, a lot of people say they use Twitter like that, but my pushback to that, and I think that's great, but my pushback is that, not everyone's on Twitter, obviously, and then you really are like even siloing yourself even more for those 5 popular kids on Twitter who keep sharing their papers and generating all the discussion. And I know that's not completely accurate, but I still see the danger of like the social media danger in general also applies to science, to Twitter, science Twitter. What is it? Twitter science? Science Twitter?
Science Twitter. Yeah. I have to say, so about a year ago, we had a lab meeting. We're like, how important is science Twitter? Like, do we need to get on this? What's happening? And so we got accounts, and we've been, first you just watch and see what's happening, and every so often you're brave enough to put something in the stream and see how it's, and I have to say, I think it's got more benefits than costs. I think if everyone were on it, it would solve a lot of the problems you mentioned. Like not everyone is on it. I thought it could be a replacement for getting emailed tables of contents, and it is a bit, but I keep abreast of the literature in other ways, not just through Twitter. Yeah. But amazing conversations happen. Like a paper came out in Science on the dimensionality of object representations in mouse cortex. And then the conversation amongst the people who are trying to understand what was going on. I mean, I have access to that in a way that like I would never have had before. So I generally think that the benefits outweigh it. And one other plug, this is for young researchers who might be listening. So also on Twitter, there's this new, I don't know, trend to when you publish a paper to not just tweet the link, but to do a thread that walks through it. And, I was looking at one, and I follow a bunch of CS people because I don't go to those conferences as much. So I was watching one, and it was on like,
what computer science is that?
Yeah,
CS?
I follow a bunch of
No, that's okay.
Yeah, computer science people, machine learning people, and I saw one paper and a really, really clear tweet thread on it. Like I was like, not only is the work cool, but the way they talked about it was super clear. And I looked up the guy who was a postdoc over at Stanford, invited him out for a lab. He gave a great talk, gave him a job offer on the spot.
Wow.
Like, so young people, I think it's really important to get out on science Twitter just because the visibility is important and can lead directly to jobs.
And outsource your tweets so that someone writes them quite well and clear.
Well, no, the idea is to hone the craft, try and we would do this legit, authentic science Twitter. We'll go for that.
Yeah. I mean, while we're on Twitter though, so, whenever I get on there, because I use it to promote the show and I don't do a lot of back and forth because mostly I don't care what people are saying on Twitter, but that's probably my fault for not having the right curation,
It is a curation.
It is, but
problem.
I don't want to spend months curating the thing and then constantly wonder what I'm missing and what I'm doing right. Because I still feel like no matter what, I am giving up. I have a lot to do during the day. I'm sure you do too. And I am completely giving up my attention to someone else's whim when I go on Twitter. And that really bothers me. So
yeah, interesting.
There's a balance. There is a balance between the...
There is. I mean, I think so. Sorry, I like I said, we had a whole discussion. We have lab meetings on Twitter and how to use it effectively and if it's worthwhile. So I thought a fair amount about this, and I think that effective curation. So your science Twitter. I don't follow anyone who's talking about politics. Right. I make sure it's about science and it's a group of people that I like to see what they're posting. And then the other thing is I don't. You have fear of missing out on opportunity costs. And I understand that. So I just don't use it during those times. I use it when I'm standing in line.
Yeah.
Or when, so I've just gotten, and I don't expect it to be a complete survey. So when I change my expectations of what it gives me and I use it in times when I wouldn't do anything else. In fact, I'm like, sweet, look, I'm following the literature. I'm getting more work done. So I've used it as a productivity boost. When I use science Twitter, I'm like, oh, look at how broad a literature I'm able to view while I'm standing in line and waiting for my coffee. I can learn about science at the same time. So I think that's you have to find your mode, and it can definitely be ineffective. And so I think that, but for where I've landed, I'm very specific when I use it and when I don't use it, never during the workday. And usually I just don't really go on it during the workday.
Yeah. Well, that's smart. I probably should stop trying to keep up with the literature in between paragraphs while I'm reading to my children at night, before bed. Yeah. And then Benny the Bear, what about this causality? Yeah, no.
I definitely know exactly what you're talking about. Well, I've read, I've heard Cat in the Hat how many times?
Yeah. Sure, your mouth moves and the sounds come out, and you can do other things.
That's right.
Well, I'll delete all this. I'll delete all of this from the show.
Yeah, that's right.
Okay. All right. Well, good luck at your conference talk, and it should be a good time. So,
thank you.
Mitchell, Seth, Kyle, Slava, and Claudio. Guys, thank you for your support on Patreon. I was going to record a little song for you on the guitar and sing to you, but my wife said that wouldn't exactly be a gift. I could just divorce her. I do like that song. Anyway, thanks guys. You can support the show by going to braininspired.co and clicking on the red Patreon button there. All right, so let's talk about how you're turning the world of visual neuroscience orthogonal, let's say.
Great.
Yeah. So you kind of mentioned this a little bit earlier. People used to think, and I can't remember who, I don't have the source for this, that our visual perception could be due to us shooting things out of our eyeballs onto the world, onto objects in the world, right?
Yeah, an early view. I actually don't know either. I should know. I
used to know. There's a really good book. Anyway, but apparently that's also a normal part of development that, when you're younger, you don't know whether light's coming in or whether you're shooting out. I actually asked my daughter this. She's 6, and her answer was I could not understand what she meant, her perception of what is happening, if light is coming in or if she's shooting it out. But so anyway, I'll try on that a little bit more. And it's kind of actually hard and a fun experiment to sort of put your Cartesian hat on it and try to get rid of all your assumptions and think, what would that be like to think, get rid of all your prior knowledge, to think that I'm shooting things out? How would that work, even? So anyway.
I know. It's true. Actually, I saw a paper by Michael Graziano on this, where he actually showed evidence that people really do have this internal model that like they are sensing the world, like in the same way that you reach out and touch things, like your eyes reach out, that's the, the percept, our internal models of our vision is one of much more of an active reaching force than a sensation.
Nicholas Humphreys talks about this too with his like reading, and I've been reading Michael Graziano's like attention schema theory stuff. And Nicholas Humphreys' soul dust. Anyway, that's not how it works, but maybe that's our conscious experience.
That's how we think it works, which is interesting. But
we know better. So I'm So I'm looking at you, which means that your image is, hitting the back of my eyeballs, hitting my retina. It gets transformed down nerve signals. It shoots down the optic nerve. It makes a pit stop in the part of the thalamus, the lateral geniculate nucleus. And then it gets relayed to our cortex in the backs of our brains, in the earliest visual cortex, called V1. That's the classic story. Well, that's how light essentially mostly comes in through the eyeballs and gets to our cortex. So maybe I'm going to let you take it now and say, what is the classic story of ventral and dorsal visual streams? Just where are they in the brain and what's their function?
Right. Okay. So once the visual information hits the cortex, the sort of classic story is that it gets relayed down 2 pathways, the ventral stream and the dorsal stream. And those have classically been ascribed the functions of recognizing what something is in the ventral stream and where something is in space in the dorsal stream. And along the ventral stream, the classic framework involves a series of hierarchical processing stages. So we think of V1, which transfers information to V2 and V3 and V4, and then into inferior temporal cortex or occipital-temporal cortex, depending on if you're in the monkey or the human. And that it's across those sort of hierarchical information transformations that you go from patterns of light into meaningful representations of objects in the world. That's a classic view.
And so in my experience, like the what pathway has really dominated neuroscience. And I guess my own research had more to do with the where pathway. And so I always wondered why that was the case. Why does what get all of the attention? I mean, obviously we need to recognize objects, but we also need to know where they are. And I'm not complaining. I'm genuinely curious, like why that is the case, and even in deep learning as well.
Yeah, I don't have a good answer, but I can just make something up on the spot, which is it might be an easier problem to get off the ground, because you can get pretty far just looking at like pixel correlations and image statistics. And the question of where immediately gets into body coordinate frames, hand-centered, eye-centered, far from me, spatial time. Like, it's actually a really complicated problem. And I also think that now that we've gained a lot more information about what, measurements from dorsal stream, I think that we might have been off a little bit more in understanding what the dorsal stream does. It does way more than just where is something. In fact, it's got all kinds of object information about what something is. You can decode object category from the dorsal stream almost as well as the ventral stream. Not as well, but almost as well. And in some cases, like high abstract things, people have found that you can decode like face identity in the dorsal stream. These are radical things if you're in a classic view of it's all about spatial information. So I think we made progress on the ventral streams. We're a little closer to like in approximating what its function is, and that problem might be a little easier on a first pass. So that's my guess.
They are distinct anatomical pathways. I mean, there is crosstalk, of course, but even when you hear someone just say, I study visual processing, and it's assumed that they're
It's
studying the
assumed
ventral.
it's the ventral stream.
Yeah, strange.
That's right.
So.
Yeah, it's true. I think if you think about it, we're like tracing the signal in and understanding the retina and then going to V1, and then we're making our way, and we're just sort of like the front edge of sort of tracing the sensory signal and trying to get as far into the brain as we can. And you get a little farther in the ventral stream visually. Like the dorsal stream ends up taking less obvious visual characteristics pretty early, whereas ventral stream you get pretty far.
Damn it. Everything I did slowed my career down. Yeah,
that turns out dorsal stream is a trickier beast. But we are making progress on it. I think that we're not too far off from a revised view where I think people are realizing that dorsal stream representations are so much more interesting and multifaceted and multiplexed and abstract. And I think that those frameworks are coming forward and the classic view is going to be updated.
Well, you're helping that happen, essentially.
I try.
So this classic view, right? You already said it. The ventral stream, in these really early visual areas, you start with these really low level features like little edges and lines and orientations. And then as you process up among the visual hierarchy, they become mid-level features like smaller shapes and things like that, or not necessarily smaller, but shapes and things like that, until you get to the peak of the mountain, and there you have grandma, or there you have the object that my grandma's at the peak. So there you have the object that finally gets encoded, and the visual cortex has done its job. And and that is one way to look at the map, right? That hierarchy, and you have turned it on its side, which is why I said orthogonal.
Yeah.
And I don't know how do you want to just start talking about how like topography in the brain, or I'm going to let you just take it and talk about the difference.
Okay. Yeah. So that's right. So if you think of we'll just simplify the visual cortex as a two-dimensional sheet. And what you just described is one axis going from the posterior to the anterior bit of the underside of the brain, where we think that sort of lower level features and then mid-level features and then higher level features are sort of extracted en route to recognition. And that's sort of a one-dimensional story, low, middle, high. Mm-hmm. But what I've been trying to understand is within the level, what are the major divisions there? So not just sort of what's the level of abstraction, but what's the nature of the tuning? And is there any systematic structure in that? And one thing that we found, we sort of back-ended into this result really, but that story about the hierarchy just doesn't make any predictions about whether some kinds of object information would be represented here in the cortex and other kinds of object information would be represented here, like animate shapes or inanimate shapes. It just doesn't have anything to say about that. But we know from brain imaging that the spatial structure of those response preferences is highly consistent. It's consistent across individuals. It's even consistent across species. So we sort of haven't had the theories have been sort of absent on that. Why is the topography the way it is? Yeah. And so just in trying to so the first step was just let's make a map. We know object information drives this whole cortex, but are there any divisions of objects that drive different parts more than others? And one of the sort of major findings we have in terms of trying to understand this large scale structure is that the distinction between animals, between big objects that are useful for supporting your body or navigating around, and then the distinction with small objects, so manipulable small things, that three-way division is mapped out across the cortex. So you can see just a zone of cortex that responds more to big objects than the other categories. And it runs all the way along the hierarchy. And right next to it is a zone of cortex that responds more to pictures of animals than the other categories. And it runs all the way along the hierarchy. And same with small objects. So there's this systematic structure that's orthogonal to the hierarchy. And that's just the data. We're so there's clear structure in it. And then the interesting thing is trying to understand why. Why, yeah. And what does that tell us about the nature of the tuning?
Well, so you call this the tripartite organization of which is a good name. And what you just described makes sense. It's not what you guys expected to find.
No.
And it's interesting because the order of it kind of from, I guess, dorsal to ventral or medial, it goes big. Yeah. Anyway, the order of it goes.
It's weird. It's big, in a weird order.
Yeah.
Big
and inanimate object.
Animals in the middle.
Animals in the middle, and then small
objects.
Things.
Yeah, and then animals, and then big objects. It's this mirrored tripartite organization. It's super systematic and not at all what we expected. So, yeah.
So you've done, so that was like the sort of the major finding that then you've taken that and run with it. And you've done a bunch of experiments to see what's going on here.
I know it turns out that like just that initial finding had a lot of questions. Like, that's a lot of cortex for animals. Is it all doing animals and big objects? No, probably there's different features underneath. And so one of the findings we had was that, so this is this idea, we call it content channeling, which is, it's a different way of thinking about how you need to get information from the input to meaningful representations of the world. And rather than thinking of trying to extract low and then middle and then high level features, you try and go, given these high-level distinctions, like between animate and big and small objects, what's the systematic structure in the input? What are the covariances that let you get from patterned light up to those? And so the idea is, it's not, big objects tend to be more in your periphery and recognize more in your peripheral, and small objects, you tend to hold them in your hand and they're at the center of gaze. And, if they're out in the periphery, you don't even recognize them anymore because of acuity limits. So there's there's a really early joint between just the angle that it subtends in your visual field and the size of the object. And that's just a natural covariance that small things tend to have smaller visual angles and big things tend to subtend bigger visual angles. And the visual size of things is something that's mapped in early visual cortex. So there's like the beginnings of a natural way to start to separate small objects and big objects just from a very early signal. So that's an example of a covariance between like a high level property and then a low level input. And so our idea is that what the visual system is trying to do is figure out what covariances there are between the input statistics and the high level statistics and make these channels that run through them. And sort of channel information from patterned light into, the useful, contentful representations of the world. And so that's what we think is going on, across the hierarchy in this orthogonal way.
And it's interesting, the way I described it earlier, you get to the pinnacle, right, of your visual processing, and then there you have the object. But of course, it doesn't stop there because we have all of these behaviors that we use objects or representations of objects for. And part of your story, and I know I'm jumping the gun a little bit here because there's a lot of other stuff to get to, but part of your story is that this content channeling essentially could be used to communicate with broader regions in the cortex that are doing evolutionarily beneficial things, essentially, or ethologically beneficial things, and that it makes sense along this channel, let's say for big inanimate objects, that it might be, and this is just one example, connected more broadly to navigational systems. And this is why these covariant properties along this stream would be useful in this region when they're connected to navigational.
Yeah, you nailed it entirely. Basically, these divisions, I think, interface with sort of major joints in our behavioral repertoire, manipulating tools, navigating around the world, and interacting with other agents. And the idea is by separating those out spatially on the cortex, it makes the wiring problem easier. So if you want to get this visual information into other systems, long-range networks only have to come in and they can synapse on this part of the object responsive cortex to get to navigation and this other part to get up to sort of reaching regions. And so it kind of, by sort of spatially elaborating these distinctions, it makes the topography or the network wiring much easier to get information out of the visual system into, these more amodal or behaviorally relevant networks.
I mean, I have so many questions about this. So one of the things that you use to do tests, to experiment, to get at these questions, is you use what are called text forms.
Yeah.
And this is sort of to study them. What's so funny about that?
It's funny because we made that word up.
Oh.
And we spent years trying to figure out what to call them. And then we finally landed on text forms. And so when I hear people use the word, it brings back all the years of pain trying to figure out a snappy name for them. And like, look, there you are saying the word text form, something we made up. So that's good.
There you go. Well, so text forms is short for something. So you can tell us that, or it's a conjunction essentially.
Yeah.
So what are they and how do you use them? And what do they fit in the story?
Yeah, that's right. So text forms are these stimuli we made by using
She's smiling. She can't help but smile when she says text form.
No, it's just a made-up word, but I love it. That preserve the texture and coarse form of the original image, hence the word text form. But the critical thing about these stimuli is they're not recognizable. They look like textury blobs. They're interesting, but you don't know what they are. And that makes them a really interesting stimulus to use because they clearly have some of the structure of the visual object that it was generated from, but they're clearly missing features that, for instance, let you recognize it or give you a sense of its 3D form. Like they don't have clear contours.
Yeah, you can't tell what it is.
You don't know what they are.
After you show someone what it actually is, can they tell then? I can't remember.
Not very well.
Yeah, okay.
We're working on training people so that we can see what happens when you can associate. But anyway, I digress. Okay, so these text forms are interesting because they let you see what happens in the visual system, like what regions are even driven by these texture and coarse form features. And the classic hierarchy theory, and certainly what we expected going into this, is that maybe we'll drive some of the posterior bits of the visual system, but we won't make it all the way up to the anterior bits where high-level representations are because these aren't recognizable stimuli. And so how could they possibly drive those high-level regions? And then what we found is that they drove the entire visual cortex the same way.
Crazy.
So even though you're looking at textury blobs of things, the textury blobs that were generated from animals still drive the cortex that represents animate information more than the other ones.
These are not the neural correlates of consciousness, for example.
Right. Well, there are differences between them.
Oh, is that right?
But like they're a little bit weaker throughout. Mm-hmm. But so it's interesting. So there are differences, but it's not like they stop and they don't make it to the anterior bits. So exactly what you make of this, people are debating. But where we've told the story is that I actually think that those anterior bits that we call high level are actually a little bit more mid-level and primitive than you might think. And one of the reasons why I think this is true is I think a little bit obvious, which is we can't have a new neuron for every new category. Right? At some point, that's just not a viable coding solution. Like, oh, I learned a new category. I need to grow a new neuron that connects in a certain way. Like we need so usually, and I think this is kind of a general rule of organization. I'm going to a slight digression here. Like if you go to the grocery store, things we're buying food to make meals, but they're not organized by meals. They're organized by ingredient, one level down, because to make a meal, you need different ingredients. And sometimes I wish restaurant or grocery stores were organized by meal, but then, you can see the problem is how do you find which meal you want? There's a gazillion meals. So this is like generally the level you want is not the thing you code for. You code one level down. And so what I actually think may be going on in the ventral visual stream, especially in those anterior bits, is they're a little bit more primitive building block features. And then they can be used to make any object, but are specifically useful to make the sets of objects we see in the world most of the time, and particularly to emphasize the distinction between animals and big objects and small objects. So their tuning is primitive, but they're organized spatially by these high-level distinctions. And so that's kind of a nice property. It means the features themselves are mid-level, but long-range regions can go in and listen to part of this cortex and effectively be pretty sure that there's probably an animal there because those animal-like neurons are the ones that are firing. Right. So I think there's a nice way to go from like mid-level features to high-level content all in one go.
It's like the Lube of the channel or something. allow the early processing to seep into it and allow the higher level processing to go and grab it.
Exactly. So you have like a mid-level buffet and high-level readout.
Yeah. Nice. Yeah. So you use these text forms. One of the interesting things about the way that you use them is you have people sitting in front of a screen and you're showing them these text forms. But of course, on the screen, the text forms are all the same size. But in real life, you're looking at an object of, say, a blue whale or something, which is huge. Well, no, let's not use blue whale because I want to ask about that later. A barn,
a piano,
right?
A barn, yeah, okay.
Or a piano. But and it subtends 5 degrees or something, 10 degrees visual angle, and then you look at let's say, I don't know, a mouse or something like that, and it subtends the same amount. So you're controlling for like the actual size, but the processing is still within these channels in the brain.
That's right. There's like this beautiful exchange that happens between early visual cortex and occipitotemporal cortex. So in early visual cortex, the dominant spatial organization is by retinotopy. That is visual field maps. So these are even used to define the hierarchy in the first place. V1, V2, V3 are defined because they have separate maps of the world at a large, or the visual field at a large scale. And then right past that, things start to change, and the responses seem to be organized more by what things look like rather than where they are in the world. So you start to see object-centered responses that care more about like curvy things versus boxy things, no matter where it's positioned in the visual field or how big it is in the visual field. So there's this like beautiful transition between cortex organized by space and then cortex organized by shape. And how that magic happens, we don't know yet. But that's just in the empirical data. You can just see that there's a switch that happens there. And so we happen to be in the cortex that's sort of abstracted away from the retinotopy as the dominant organizing factor, and we start to see responses that are more object-centered. So they care about, like, big objects have systematically different shape structure than small objects. They're boxier, they have larger surfaces, they have more high spatial frequency. There's all this structure that's related to the fact that to be big in the world, you have to have certain shapes, withstand gravity. And so I think that's the kind of features that these, neurons and brain regions are picking up on in a way that's abstracted over the sort of initial retinotopic stages.
Oh, there's so much to do.
So cool, right?
Yeah, it's so cool. Yep. And there's it opens like so many different, like all good science, you answer one question and it asks multiple more, essentially.
Yeah.
Let's take a little break for the quote of the show. When you see something that is technically sweet, you go ahead and do it, and you argue about what to do about it only after you've had your technical success. That is the way it was with the atomic bomb. That would be J. Robert Oppenheimer. So you have shiny new toys and deep learning, and one of the things that you do is test. So let me back up. So I've had Dan Yeamans on the show.
Oh, cool.
Yeamans, I think it's Yeamans. And he, with Jim DiCarlo, were responsible for making some of the early Deepnets that sort of mimicked the classical hierarchy of ventral processing, where these early layers. So when you teach one of these deep convolutional neural networks with various different layers. If you teach it to classify images, when you look at the units and the different layers, they map on pretty well to the ventral visual stream as far as low-level, edges and things, and then mid-level shapes. I don't know if text forms are in there, and then...
Yeah, we've done it. Yeah.
I know. Well, that's what... So, but so that classic hierarchical story has been recapitulated in neural networks. And part of what you've done is you've tested your story, and tell us what you found.
Yeah, I think when we did a couple of things, so we sort of replicate what people find that like deep neural networks do a pretty good job of predicting responses in human ventral visual stream with our stimuli. But then we also could do something fun, which is show the text forms to Deepnets and see, what happens. And I actually remember when my postdoc and I were thinking about this, he was like, I don't even think the text forms are even going to drive the Deepnets. Like, shouldn't we fine tune first? I'm like, no. Just show them the Deepnets and see what happens.
What was your guess?
Show them the text forms and see what happens. Well, I don't know. I just knew that the right thing to start with was to see what happens.
Okay.
And what happens was, the Deepnet thought they were all plastic bags, but the responses at the different layers also did a reasonably good job of matching the responses to text forms. And what's cool is those same responses did a good job matching original recognizable image responses as well. Not as good, but like 80% of the way there.
And these were sort of the mid layers of the convolutional neural network.
Yeah.
But that was stretched over a broad region, showing that a lot of these different layers actually represented well this mid-level sort of form.
That's right.
Yeah.
So we've been unpacking that. So people have spent a lot of time, again, focusing on the hierarchy. Different layers of a Deepnet correspond to different layers or sort of regions along the hierarchy in the brain. And that result is real, but it's a way blurrier hierarchy than I think people think. So when you've done it yourself, you see that, layers 4, 5, and 6 of Alex and that, like they all do pretty good across much of this cortex. So it suggests that this idea that each region of the brain and each layer of a Deepnet is representing information in a completely different way, that just doesn't turn out to be true. And even direct measures on a Deepnet to understand how similar are the layers to each other also bear this out. Like those mid-levels in a Deepnet are also pretty similar to each other. There are slight changes because it's getting better and better, but there's a bulk of those layers that have pretty similar kind of responses. So I think this also sort of is compatible with the content channeling idea. Like, instead of it really being about isolating separate levels of representation as you go along the hierarchy, it's more about like twiddling and trying to match the covariances to untangle the retinal input and align it up with the content divisions at the top. And sometimes those representations are going to be kind of similar to each other, slightly different, but pretty similar, which means it's going to be more of a blurry gradient, a blurry hierarchy. I don't know if that made sense, but you go.
But that touches on the topography of that exists in the brain just because of wiring constraints, that things near each other tend to code for the same things. And is it the case that deep networks don't have that topography because there's just not a limitation on their wiring?
Yeah, this is like one of my current favorite topics, which is how should we bring topography constraints into Deepnets? In a way, they have some of it. The convolutional part of a Deepnet has an implicit topography in it. But for instance, the fully connected layers, like that's a lot of wires from one neuron to all the other neurons. Yeah. And, maybe we should have some constraints on the number of wires or how sparse the connection should be. And so there's a lot of different ways of bringing topography into Deepnets. Another one is maybe we should unpack the convolutional assumption a little. That assumes that the features that are learned apply equally everywhere in the visual field. But a lot of the theories about why the cortex comes to have this organization depend on, say, different features in the fovea compared to those in the periphery. And a Deepnet can't learn those, so we might be missing some structure there. So yeah, exactly how to build topography into Deepnets, there's a lot of interesting ways. If you're interested in a postdoc in doing these things, to anyone who's listening, I'm always hiring.
Yes, all right, I like it. Where should I apply? No, just that's great. So there are some. In the interest of time, I kind of want to wrap up soon with this push here. But so there's the evolutionary question, right? Mm-hmm. And maybe you can just tell us what you think it all means, and speculate like what and why.
Yeah, I mean, I think that right now in visual neuroscience, there's like a lot of interest and excitement in trying to figure out why the organization is the way it is. Why does it take these forms? Why do some regions end up where they do systematically, and what tuning do they have? And there's sort of two camps, maybe three. The main camps are the people who are on the empiricist side, who think that it's all the structure of the input and a sort of generic architecture, and all of this beautiful structure and the separation of different object categories can emerge just from the statistics of natural input.
Right.
And they are doing things with, there's modeling that can test that. And they're also sort of, raising baby monkeys to see and show that like early experience with new categories can lead to like new regions that are formed, like clearly showing the role of early intensive visual experience in the large scale structure of the cortex. So that's one side. And the other side are the people who think more of that structure is built in. Why is it, tripartite? Well, these are not arbitrary distinctions. And navigation, manipulation, so like these are critical joints in our behavioral repertoire, and network architecture, like long range network connections. Yeah, those don't just grow when you're a baby. Those are built in. Those are patterned. So on that side, like the structure of the network might be set up to enforce particular kinds of content divisions that are useful. And so that's the idea. Well, like, would these divisions just be learned naturally, or are they enforced by particular readout structure? Then now that's a sort of a tractable empirical question. And the third camp, this is one that sort of I'm in, and I think it's received a little bit of less attention. And that's just that maybe the structure of this object selective cortex is emergent itself. It's maybe loosely constrained by the input and loosely constrained by the readout, but largely is related to just the similarity structure of things in the world trying to be mapped smoothly on the brain. And so that again also leads to testable predictions. Maybe you don't need either of those constraints to kind of see the organization that we're seeing. So I think that there's pretty exciting computational approaches to sort of getting at, well, how much can you learn from the input? How much do you need to build in? And how much can be reflected from sort of a smooth mapping of the shape structure itself? And that's sort of where we're going next.
This is also just a broader question of cortex, and, is all cortex the same? Obviously it's not completely structurally the same, but essentially it's the same. A lot of people argue, so it all must be doing the same thing. So that would be, I guess, the empiricist side of So
yeah, I kind of think that there's two kinds of cortex. There's the kind that's a little bit more sensory, and there's the kind that's a little bit more, I want it abstract for a better word. Like, and you can kind of see this in the nature of lesions. So if you get a lesion in the back of the brain, you can't see this part of the visual field, or you can't recognize that category of objects. You get a lesion in the anterior temporal lobe or the prefrontal lobe or some of the parietal bits, and it's hard to map what happens. Like they don't signal information in the same way. They participate in a more associative and sort of dynamic representational scheme, whereas I think the sensory areas are a little bit more fixed and labeled. Like this neuron, once it comes to code for faces, like that's what it does. It doesn't code for anything else after that. And so I actually think the visual system along the ventral stream, we have this sort of labeled line, like what it fires highly to, it's actually signaling that content is present. And then it just interfaces with the cortex that's now going to make more interesting combinations of those. And that's it. I think that's a different kind of cortex. And, maybe it has different kinds of connectivity motifs. But I don't know the answer to that. But anyway, from seeing the data and different lesions and the consequences they have, it seems like there is a sort of maybe evidence for at least two really different kinds of coding schemes in how cortex represents information.
God, you just opened a huge box that I want to jump into. But, all I'll say is someone like I might have thought that you had divided into three. That's all I'm saying, instead of two types of coding.
Interesting. What's the third?
Well, I don't know. That's for you. You have to, maybe.
Oh, you mean because of my tripartite?
Yeah,
Yeah, I have to think more about that now, huh?
There you go.
That's a good point.
Yeah. Just don't limit yourself to two. That's all.
Yeah, you're right.
We do tend to do that. Well, okay. So quickly before we move on, because I want to ask you some broader general kind of questions here, but back to my beloved dorsal stream.
Yes.
So, you took this longitude and added latitude. Let's just to be quick, we can say, to put the new scaling in to complete the map, essentially, in the ventral visual
Yeah,
stream.
it's the other side of the map.
And the other side of the map.
Axis.
Is there something to be learned in the dorsal stream from this type of approach? Or do you not want to touch that?
Oh, it's good. I mean, one of the reasons why, so yes, the short answer is I definitely think there's something to be learned by mapping the cortex, as long as you're in cortex where the maps are stable. Like I'm saying, there seems to be cortex where that's not true.
Right.
I don't think it may not be as helpful there, but in certain systems like motor cortex and, ventral visual stream, the maps are stable. And so studying them seems useful. I think that one of the reasons why I haven't looked in the dorsal stream too much is because, mostly when you show people pictures of objects and have them do boring tasks like, detect a repeat or a red frame or the fixation changing color, you just don't drive the dorsal stream that much. But then I just recently did some new work with my student who got a bunch of videos of people performing everyday actions, little short videos, and we tried to span the set of things people do. And we showed...
Looked at the Andy Warhol archive or something?
Well, how we collected it is another story.
Okay.
We started with verbs, but verbs ended up not being useful. So then we went to the American Time Use Survey, which was literally a survey where they called people and asked them what they spend their time on. And anyway, from that, we picked out common everyday actions.
Wow.
Heaps of work.
Yeah.
My graduate student has made a heroic effort on this. Yeah. Anyway, so we collected all these videos and we scanned people while they are viewing them. And not only do you see beautiful activations all along the ventral stream, but the dorsal stream, just the whole thing, all the way along the intraparietal sulcus, all the way wrapped around to super, it's just beautiful activations. And I just had never seen that before. And it made me realize that, to study the dorsal stream, it's going to be, you really have to pay attention to action and people performing actions. And that's a different world than curvature and texture and
curvy
coarse
boxiness.
Form information.
Yeah.
And so I think I haven't tried to take on that feature space yet, but I've started to see what makes it go, and it's people doing things in everyday settings and makes it go crazy. And so something there, but then again, so many things drive it that maybe we need completely different theories, that maybe the theories of the ventral stream really don't apply to the dorsal stream in the same way. So I'm going to say, I'm going to keep focusing on the ventral stream for now, and we'll get to the dorsal stream next.
Okay. All right. Well, so do you have time for a few bigger general questions?
Yeah.
Okay. One, just related to what you're just talking about. What is something that you see that is just wide open right now for someone, who wanted to sort of get into this and doesn't want to compete with you, what in neuroscience and or AI do you feel is just wide open and ready for the taking?
That's I think there are a treasure trove of insights in neuroscience and cognitive science that can be assessed with a new lens by being a little bit creative on how you use Deepnets, comparing Deepnets with and without this architectural motif, or there's insights in mid-level vision about border ownership cells and some beautiful neurophysiology, and I don't know, there's just a whole area to can we, they have thoughts about the models. But that was pre-Deepnets. So I think just treasure trove of neuroscience insights and thinking about clever ways to probe how those work with both human behavior and human neural responses and Deepnets. I think there's so many. So I think finding the question or the facet of, visual cognition that you're most interested in, and then sort of exploring how to implement that smartly and how to gain insights using these new modeling tools is an easy one.
Yeah, no, that's good. So that is sort of using the AI almost as a tool then to answer questions about neuroscience.
Yeah, that's true.
No, I'm not knocking it. But my question is, what aspect of neuroscience do you think will have the biggest impact on AI moving forward?
Yeah, I don't know if I have a great answer to that.
All right.
I think AI has the advances in artificial intelligence impact so many fields. They make contact with so many fields that neuroscience can influence a facet of AI, but it's going to many fields. So yeah, I don't know.
Gotcha.
Yeah. We can skip that one.
No, I think I'll leave it in. What's something you used to believe that you now think is naive?
Yeah, I remember. Okay. I remember thinking about how visual experience shapes the cortex and sort of thinking that it was sort of plastic and related to experience. Stop. But what I now realize that was naive because I didn't appreciate the role of intensive early experience in shaping the large scale topography. And it's really only intensive early experience that's involved in shaping these maps. You can learn new objects just fine as an adult, but they don't give rise to large scale map like changes. They lead to little tweaks in the weights that you can measure, but they're very subtle. But if you train, kids or baby monkeys to learn new things, you see these huge changes. And so I think it was naive to think that visual experience has an equal impact at any point. And now I appreciate just how intensive early experience is going to be where the answers lie for why the large scale topography is the way it is.
How would you proceed if you had to start over?
That's interesting. I mean, I'm going to reinterpret that question a little bit to be like, if I were starting now, what would I do?
Sure. Sure.
Which is, I think, a lot. And the reason why I'm reinterpreting that, because I think I got pretty lucky that in my undergraduate, I took a lot of math and computer science in addition to cognitive science and neuroscience. And that paid off.
That's skill. That's not luck.
Well, I mean, they were my interests and I followed them. But not, that I had other interests too. And, you only can follow some of them. And if you have a tendency towards the computational side, I would say start early and dig deep. And, to the extent that I wish I had done that more, that's mostly where I have regrets. It's like, I wish I knew even more. I wish I knew even more of that because because it's like the CS, computer science fields and neuroscience fields and cognitive science fields have towers of knowledge, and there's just so much room to string bridges across if you can speak their language. Yeah. And it's a translation problem, if anything else. And the only way, it kind of ties back, the only way to be fluent is to get it early so that you speak all the languages. Yeah. And it's harder to get that later. And if you can immerse yourself now in all of the disciplines, I think the potential upside is very high.
That's basically what Mate Lengjo said as well. So that's good. That's two
good.
Times now. Yeah. He didn't say it as eloquently, I have to say. Okay, last one. No knock against him. He's a very eloquent person. When will we look back at the mystery of consciousness and wonder why we took so long to get it?
I mean, I feel like we have a microcosm of the answer to that right now, because I think it was like 2 days ago or something, a week ago, there was that problem in computer science about specificity of and or gates. And it had been like a problem that the who's who of math theoreticians and computer scientists had tried to solve, an outstanding problem for 30 years. And then, as of 2 days ago, it got solved in a 2-page paper. That's so easy and elegant. Everyone can understand it. And, the news article I read on it said, this is going to be taught in every introductory class now, because that's how easy it is. Huh. It's a paradigm. Yeah. And so I think that when we finally understand consciousness, I hope it's a little like that, which is, it seems like such a hard problem and people have worked on it for so long. And then when we finally get the answer, it's 2 pages and we'll not understand why we didn't see it before that.
Love that answer. Well, Talia, this has been really fun. I know we are out of time and I can't ask you about using blue whales as navigational tools. So that'll have to wait until, I'll have to wait until I buy you a beer next time when we actually meet in person or something. So
it's ECN.
Yeah, hopefully it's ECN. We'll see. No. So I appreciate your time. Have a great conference, and thanks again.
Thank you very much for having me.
Brain Inspired is a production of me and you. You can support the show through Patreon. for a microscopic $2 or $4 per month. Go to braininspired.co and find the red Patreon button there. Your contribution will help sustain and improve the show and prohibit any annoying advertisements like you hear on other shows. To get in touch with me, email paul@braininspired.co. The music you hear is by The New Year. Find them at thenewyear.net. Thanks for your support. See you next time.